Okay, let me welcome you to this second lecture of our reinforcement learning course at ASU. We talked last time about deterministic dynamic programming problems. And today we're going to talk about stochastic problems with finite and infinite horizon. So here's the outline. We're going to do some review the dynamic programming algorithm for a finite horizon deterministic problem. Talk a little bit about approximation in value space and also give an example of rollout. Then we're going to talk about the stochastic version of dynamic programming algorithm where the dynamics involve a stochastic random disturbance. Then we are going to talk about an important, nice special case, the case where the system is linear and the cost function is quadratic, a very important case, a very important problem in control theory, and also one that has an analytical solution and will provide us with a lot of insight for more difficult problems. We're going to take a break and then talk about infinite horizon. We're going to overview the theory and the algorithms and return back again to the linear quadratic problem. So let's get started with review. We talked about this deterministic dynamic programming problem involving n stages, whose state begins at time 0 and goes all the way to the last stage, n, and the state is denoted by x0, x1, up to xn. The state evolves under a sequence of control. At state xk, we apply control uk, and we move to a state xk plus 1 according to an equation. And the corresponding cost for that stage is denoted like so. Now, I mentioned last time, and I'll emphasize again, that our formulation allows arbitrary state and control spaces. So the state can take a finite number of values or an infinite number of values, and similarly for the control. That's one of the nice things about dynamic programming. It applies, the main ideas apply in great generality. Okay, so given a sequence of controls, there are all these costs generated, and there's also a finite state cost. And this is our cost function. And what we want to do is for a given initial state x0, minimize over all control sequences this cost expression, the total cost. Now, for every sequence, this sequence of controls, this cost is defined. It's a function also of the initial state. And the optimal cost function is obtained by minimizing overall controls, this expression. And it depends again on the state x0. We use J star to denote optimal cost, or anything optimal we denote by star in this course. Okay, so this is a problem. And we talked about the dynamic programming algorithm for solving it. And the dynamic programming algorithm focuses on calculating the optimal cost of the tail subproblems, all the tail subproblems that begin at any stage k and for any state xk. And it starts with a trivial tail subproblem involving just a terminal state, and it goes backwards. At time k in state xk, we solve the corresponding tail subproblem, starts at xk and goes all the way to n, by simplifying as follows. For every possible control, we calculate the cost of the state, and we add to it the optimal cost of the remaining stages as calculated earlier and starting at the next state. So we go backwards, first jn star, then jn minus 1 star, all the way to j0 star, which is a function of x0, the initial state. And the argument is that this is exactly the optimal cost of the problem. We have found the optimal cost for this algorithm. And we justify, it's very easy to justify based on the principle of optimality. And there's a more formal mathematical proof in your class notes. Now, you can view this as a computation that's done offline. It's offline training. It has to be done offline because it involves lots and lots of computation. You have to do all these operations for every stage and every state. There could be zillions of states, so that can be an enormous computation. So it has to be done offline. Simultaneously, we can calculate the optimal controls as we do this minimization, but there's another option. We can calculate the optimal controls online by online play. And here we go forward and we construct the optimal control sequence. Starting at state x0, we do this calculation just for that state. And we have already computed J1 star from offline training. And we find JU0 star, and that will generate the next state, x1 star. So we go one step forward to the next state and do this calculation again, using, again, the J2 star, which we have calculated from here, and we go forward all the way to the end, and we construct the entire optimal control sequence this way. Okay, so let me interject here parenthetically the term Q factor. We're not going to use it for the time being, except peripherally, but it's going to be helpful later. If you look at the right-hand side of the dynamic programming algorithm and the term within braces that you minimize, the first stage cost and the optimal cost to go, it depends on the state and control. And we define the optimal Q factor corresponding to X, K, and UK by this expression here. And if we know these Q factors, then we can calculate the optimal costs by just minimizing here. This is just the dynamic programming algorithm with this expression plugged in here. So we can combine these two equations also and write the dynamic programming algorithm in terms of these Q factors. Okay, so the Q factor is defined like so. We take this expression at K plus 1 and we plug it in here, and we have this expression here. We minimize with respect to UK plus 1 here, and that leaves something that depends on XK and UK. And it's the optimal Q factor, and it is the optimal cost assuming starting from that we start at XK and we choose as our first control UK and act optimally after that. Now there is a class of algorithms in reinforcement learning called Q learning. This is a simple form of Q learning, but we're going to discuss other forms that involve approximations, that involve more complicated things. But for the moment, we'll just leave it at this point, that there's a Q learning form of the dynamic programming algorithm. So now let's go to approximations. We mentioned that computing J stars of K is overwhelming calculation. So the idea here is to replace JK star with some approximation during the online play phase. So here we start at, we calculate this minimum at the initial state x0, and it involves, instead of J1 star, we use J tilde 1. And then we find this control, and then we go one step forward, and we sequentially go forward from x0 to x1, x2, and so on, each time selecting a control, this calculation, which is exactly the dynamic programming formula, but with J tildes in place of J stars. So if we know J tilde, that's much better calculation than doing this with J star. But how do we compute J tilde? Well, this is the million-dollar question, and it's one of the principal issues in reinforcement learning. In a lot of reinforcement learning, what we're trying to do is find the right kind of J tilde with a reasonable amount of computation. And there are a number of different ways to do that. One way is what we call offline problem approximation. So here we use as J tilde the optimal cost function of a simpler problem, which we compute offline by exact dynamic programming. So we simplify the problem, we simplify the dynamics, we simplify the constraints, and we obtain an easier problem that we compute offline with solution. And we get the solution and we plug it in as J tilde in our original problem. That's one way of doing it. The method of aggregation is one class of methods within this category. Another possibility is to compute these values through a shorter horizon minimization, compute them online by multi-step look ahead, and also perhaps add a primitive terminal cost. And this is what's often done in model predictive control. We'll get to this kind of methods later. Another possibility is to do training using neural networks or some other kind of approximation architecture, where we calculate these J tildes by selecting them from a parametric class of functions that depend on state and also depend on a parameter. This parameter is the set of weights of the neural network, for example. And we train the neural network, find parameters that fit data, and then we plug them in here, and that's going to be our J tilde. That's a very popular method, and we're going to discuss this extensively later. And another possibility is rollout with a heuristic. And I will demonstrate this, explain it and demonstrate it, and postpone discussion of these other methods for later. Okay. So remember that what we want to do is calculate online a control at every encounter state. Suppose that we have, so what we do is we generate a single trajectory from x0 to xn by online play. And we start out at x0, and at every step we reach the state. Let's call this the current state at xk. Upon reaching it, the rollout algorithm does the following. It generates all possible controls at that state, and then from each one of those, it runs a heuristic, some heuristic, okay? We don't care what the heuristic is for the moment. It just generates a trajectory from xk plus 1 to xn, and also has a cost associated with it, the cost of the transitions that it produces from here to here. So for every possible control, we do this plus that, calculate this term, an approximate Q factor. Then we do this for this control, calculate this plus that, and similarly. So from each of the next states, we run the heuristic, compute the heuristic cost, and then out of all this heuristic cost, we find the one that minimizes this expression, and that's what we apply at xk. So here we calculate these Q factors, find the control that minimizes the Q factor, go one step forward, and then do it again. Run the heuristic again from the next possible states, and so on. And in this way, we generate a complete trajectory one step at a time. So let me give an example of this. This is a traveling salesman's example. It's the same example that I used in the previous lecture. It involves 4 cities, A, B, C, and D. And this is the matrix of intercity travel costs. And we formulated this problem as a dynamic programming problem where the states are partial tours. This is the partial tour that involves state A, B, and then C. This is the partial tour that involves A, B, C, D, and C. And it can only be completed by going to A back again. So from each partial tour, by adding a city, an eligible city, we go to a longer partial tour until we reach the end. So this is the initial state, the stage of the first stage, second stage, and so on. And the costs are given by this matrix of travel, of intercity travel. For example, to go from A to D, from A to D, there's a cost of 20, and we write it here. So these black numbers are the costs as given by this matrix. And we solve this problem by dynamic programming, exact dynamic programming. It's very simple. And we calculated these red numbers. These red numbers are the optimal costs of the tail subproblems. So this is a tail subproblem of starting here and going all the way to here. And 8 is the optimal cost to go from here to go to here. You really have to choose between these two. It turns out that this is best. We have already done in the previous lecture the dynamic programming algorithm, and we have calculated the optimal cost. Now we're going to use rollout to solve the problem suboptimally. And in the rollout algorithm that we're going to discuss, we're going to use a specific heuristic, and that's the nearest neighbor heuristic. Here we are at a given state, which corresponds to a partial tour. We look at all the eligible next cities to go to, and we go to the one that's closest in terms of travel cost. So we do that here for all eligible cities, and we run the nearest neighbor heuristic to the end and compare all these costs of the partial of these portions of the tour, and we choose the city that is best in this in terms of that cost. So what I'm going to do now is demonstrate the rollout algorithm for the problem. Let's run the base heuristic, the nearest neighbor heuristic from city A all the way to the end. Here, out of all these three possibilities, this is the nearest neighbor, right? Has a cost of 1. So we go here. Once we get here, there are two possibilities, go to C or to D, and the nearest neighbor is D. Then there is no choice, there's only one choice, and so we go all the way to the end. So the nearest neighbor heuristic generates this trajectory, which we call T0, and it has cost 28 in this case. Okay, so now let's execute the rollout algorithm from state X0. We have to generate all possible next cities, and then from each one of those, run the nearest neighbor heuristic. So let's consider this one. The nearest neighbor heuristic looks at these two neighbors, finds the closest one, and goes here, and then it goes here and goes here. So the nearest neighbor heuristic will generate this trajectory from here, and the overall trajectory is going to be this one. The red is what the no, I'm sorry. The overall, yeah, right, okay. So now we have done our calculation for next city B. Now for the next city C, we have to run again the same calculation, the base heuristic from here. Nearest neighbor, nearest neighbor, nearest neighbor. So the cost here is 28, and that cost here was 27. So we prefer this branch over this branch. Let's look also at the third possibility. We go here and then run the nearest neighbor heuristic, which is very costly. So we reject this branch. And the rollout algorithm at X0, at the initial state, goes over here. Now we do the calculation again. We look at the possible choices, C and D, and from each one of those, I run the base heuristic, which actually there's no choice, and we compare the cost of this branch and this branch. And it is this one And the rollout algorithm at this city is going to go to that city. And the overall cost is going to be 13. So we improved over the preceding choice. And then the rollout algorithm was going to move here. And then there's no choice but to go here and then to go here. So we started with a base heuristic with this trajectory. We did one step of rollout and we got to this trajectory, which is better. And then at this point, we got another step of rollout and we got this trajectory. And each time we improved the cost, and the rollout algorithm gave us 13, which is also the optimal cost, whereas the base heuristic gave us a cost of 28. So this is something that we're going to prove in general, that rollout with a base heuristic improves on the heuristic. And the way it does heuristically is because it looks further into the future, whereas the base heuristic does not explore at all this area where the optimum lies. The rollout algorithm explores more paths to city A and discovers this path at the second step, not at the first step, but at the second step. So this is the calculation, and your homework, your first homework, which is going to be due next week, is to repeat this calculation, but for a more complicated problem that involves 5 cities. Are there any questions?
Professor, can you hear me? Hello.
Yes.
Yeah. So, Professor, how does the state change from A to AB using rollout? So, what does that mean?
Okay, remember that in rollout at a given state, we look at all possible options, and we go to the next state, and then we run the heuristic for all these next states. We compare all of these trajectories, and we find the one that has minimum cost. And then we go to the next state according to the choice that gives us the least cost. So over here, yeah, go ahead.
I'm sorry, Professor. Please continue. I'm sorry.
I was going to say that to illustrate here. Here we looked at all the possible choices and ran the base heuristic from each one of these. And we selected this state as being the one that brings us to the minimum cost.
Oh, I understood. Thank you, Professor.
Okay. Any other questions?
Professor?
Yes.
Are there any assumptions on the problem that can ensure that the rollout leads to an optimal solution?
No.
Okay.
No, the rollout is not guaranteed to give you an optimal solution. The rollout, under some assumptions, which are satisfied in our example, guarantees that you are going to do better than the base heuristic. You're going to improve on the base heuristic.
Oh, okay. I see. Okay.
On the other hand, the improvement can be very, very substantial. We're going to connect this with, we're going to explain why this is so in future lectures. And notice that the calculations here are quite simple relative to, I mean, think of this example with many more cities. The calculation is impossible to do, the exact dynamic programming calculation. But with rollout, we're able to do this calculation much more simply. So it's a very simple and also very reliable way of overcoming this curse of dimensionality and the difficulties of exact dynamic programming. So let's go now to the stochastic dynamic programming algorithm, where the system equation involves a random parameter, WK, with given probability distribution. So the system evolves like so, but after you select the control, the next state is not certain. It's subject to this uncertainty of WK, and the cost also is random. It may depend on WK. Now, this WK may be several different things depending on the context. It could be physical noise like wind noise if you're dealing with airplane kind of problem. Market uncertainties if you're dealing with a finance problem, demand for inventory, breakdowns, and so on. Most problems in practice involve randomness. On the other hand, for a number of reasons, for reasons of convenience and computation tractability, sometimes we assume away the randomness and treat the problems as deterministic. But now we're going to deal with the stochastic problem. And how about the cost function? If you apply a sequence of controls, then you get cost at every stage and also a terminal cost. However, these costs are random. So to get a number to associate with a sequence, we have to, a sequence of controls, we take the expected value of this random quantity over the joint distribution, the probability distribution of all the random quantities here. And we consider policies. Policies are different than controls. They're rules to select controls. And a policy pi consists of n functions from state to control. It tells us what control to apply at any given state. So it's like a lookup table. For every possible state, it gives you the control to apply. And this is what we call a policy for a given state K, and the overall policy is the set of all policies for the n stages. This is also what we call a closed loop control because it takes into account knowledge of the current state. Also, feedback policies, another term that's used. We assume here that we observe the state xk and we act accordingly with knowledge of that state. And now that's different than selecting a priori a sequence of controls, because as we did in deterministic problems, here by using feedback, choosing controls with knowledge of the state gains us something, is beneficial because of the stochastic nature of the problem. If we choose a sequence a priori without knowledge of the state, then we don't know where we land, or we might make a bad choice. But by knowing the state, we can make a more intelligent choice of control, and there's a benefit in doing that in terms of smaller cost. That's why we're looking at policies, which are definitely more difficult objects than just controls. So now suppose that we have some policy pi, and we plug it into the cost function. We're going to get a random number here, takes the expected value of that, and then we get a deterministic number, a real number, which depends on the initial state, and that's the cost of the policy pi starting at state x0. Minimizing overall policies gives us a function that depends only on the initial state, and that's the optimal cost function of the problem. And our objective is to find J star and also to find a policy that achieves this optimum. And we are going to use dynamic programming to do so. Excuse me. So here's a stochastic dynamic programming algorithm. Like the deterministic algorithm, it produces the optimal cost of all the tail subproblems. This is the optimal cost of the tail subproblem that starts at stage k and at state xk. And we do this backwards. We start with a trivial tail subproblem at the end that involves just the optimal cost. And then we calculate the optimal cost of the tail subproblems that at stage n-1. For every state xn minus 1, we do this calculation, first stage cost plus the optimal cost of the tail subproblem at state n, which is this one. We calculate jn minus 1 star and go backwards. It's exactly the same calculation as in the deterministic case, except that we introduce also this expectation because the problem is stochastic. And the optimal cost starting at x0 is obtained at the last step. This algorithm will give you all the optimal costs from every initial state. And this is also true for the deterministic case. And this calculation also will give you the optimal policy component for every stage. At stage k, new k star is constructed simultaneously with this calculation by finding the minimum and setting new k star of xk to this minimum. So at state xk, whatever attains the minimum is the optimal control, and it's one entry in the lookup table that represents new k star. Now that's one way of doing it, but there's another way. You can view this calculation backwards as offline training. We compute all these j stars. Suppose that we have computed these j stars. We can implement the optimal policy by online play, sequentially going forwards. Observe at each state k the current state and apply the control that minimizes in this expression. In this way, we construct we implement the optimal policy online with n minimizations, one minimization at each stage. We observe the current state and we do this minimization to apply the optimal control. However, the problem is here that we need to know j, k plus 1 star. So there is no escaping that we have to do this calculation, and this can be overwhelming. It's even worse than for deterministic problems because we have to compute an expected value here for every xk and uk. So in reinforcement learning, we try to bypass this difficulty by using approximate cost functions instead of the optimal cost functions. And these approximate cost functions can be computed in a number of different ways. A lot of reinforcement learning methods deal precisely with how we compute this j tilde k. And there's also some other possibilities. We may try to approximate this expectation, which can involve substantial computation. In some cases, we may try also to minimize, to simplify this minimization here, which can be also difficult to do in many contexts. So this is the exact dynamic programming algorithm for stochastic problems. It involves a lot of computation in this offline training portion. And in approximation value space, we try to reduce this computation by using approximation j tilde in place of j star. Now, before we get into, before we go further, let's do an example. Linear quadratic problems. This is an important and favorable case. It can be solved analytically. As an example, let's look at a cruise control problem where you have a car and you want to keep its velocity constant to some set point. Now, the system equation associated with that is linear, like so. And xk is the current at stage k velocity minus v bar, which is the desired level. We want to keep this xk small, okay? the current velocity as close as possible to the desired velocity. And we have car controls that can increase or decrease the velocity. And there's also some noise. Could be wind, could be road conditions, could be a number of things. We assume that the control is unconstrained. In reality, it is not, but we'll assume it's unconstrained, and we're going to solve the problem and check whether the constraints are violated or not. And we also assume that WK, the disturbance, has zero mean and some variance, sigma squared. This is a very simple problem. In practice, there may be many difficulties. For example, many cars today involve adaptive cruise control that not only regulates the velocity of the car, but also makes sure that there's a safe distance kept from cars that are ahead. So that involves a more complicated system. It involves also constraints and so on. However, for the moment, we're going to focus on this problem, but also we're going to look at it in general and generalize in the following way. First of all, the cost function here that we're going to use involves a penalty on the deviation from the desired velocity. So it's quadratic in the state, and there's a positive coefficient that regulates the severity of the penalty. And we also want to do it with a small control. We don't want large controls or large changes in control to use in our. So an appropriate penalty is this quadratic with a coefficient r. And so that's how a linear system and a quadratic cost is generated for this example. But we're going to look at a problem that involves a generic one-dimensional system where there's also a coefficient a in front of xk. And the same cost function. And let's look at the dynamic programming algorithm. The typical step is like so. First stage cost plus cost to go from the next state according to this system equation. So we start at Jn star equals to Qn xn squared, and we go backwards according to this equation. And the nice thing about this problem is that the dynamic programming algorithm can be carried out in closed form. These calculations turned out to be easy, can be done analytically because they involve quadratic minimizations, as we will see. And this is the form of the final result. The dynamic programming algorithm gives you cost functions that are quadratic for the current state plus constant. And this kk is a number, a positive number, that can be computed analytically. And we will show how this is done. Moreover, the optimal policy is linear, consists of linear functions of the state, with this coefficients Lk also computed analytically. So linear cost functions of the state and quadratic cost. And that's the key to solving this, this problem. And it's owed to the fact that this calculation here is quadratic. Now notice another thing, that the optimal policy does not depend on the distribution of Wk, as long as it has zero mean. Sigma squared does not enter in these calculations, except here in this constant. And so even if we had a zero mean noise, there was no noise, we would get the same policy. This is known as certainty equivalence. We say certainty equivalence holds if when you replace the uncertain quantities by their expected values, the optimal policy does not change. It doesn't hold for every problem. In fact, it holds very rarely. However, often it's a common sense approximation idea for other problems. And we're going to say a few things about that as we go along. So now let's verify this calculation and also show why certainty equivalence holds for this problem. So we're looking at this system equation and this quadratic cost function, and we're going to do the dynamic programming algorithm starting from the terminal cost, which is this. Okay, so the dynamic programming equation is for stage n-1 is what you see here. Here's the first stage cost, and here's the cost of the remaining cost starting from the next state, which is this one. And we have to do this calculation. We first plug in qxn squared in place of this. We plug this in here. Then we simplify this expression by taking out the stuff that involves the random quantity w. So we expand this quadratic here, and the terms that depend on w involve the expected value, and it's this term from multiplying w with this expression and taking the expected value of w, and this expression which involves which comes from the quadratic term in w. Now this term is equal to 0 because we have assumed that w has 0 mean. This term is not 0, but it is constant. This is the variance of wn-1, which we have called sigma squared. So this calculation here gives us this, where we have taken out this term, does not depend on un-1. We have canceled out this term here, and we have, and this is the last term. And now we do this minimization in closed form. It is quadratic in u, and we set its derivative with respect to u equal to 0, which is what is shown here. And we solve for the u that sets this expression to 0. And what we obtain is the optimal policy for the last stage. And you can see that it is equal to ln-1 times xn-1, where ln-1 is obtained by solving this equation, collecting terms that involve u and solving. So this is what we have obtained from the first stage of dynamic programming, a linear policy, which we can plug in here and do all the calculations. And because u enters quadratically in this expression and is linear in x, we obtain something that is quadratic in x. It's this quadratic here plus the constant term. And after doing all the calculations, collecting terms and so on, the expression for Pn-1 is what you see right here. It involves a and b from the system equation, r and q from the cost function, and that's the expression that comes out from this calculation. So all of this has carried us through the very first step of dynamic programming, and we can go backwards now in the same way. Why is that? Because we have obtained a quadratic cost to go at stage n-1, which has a similar form to this quadratic that we used in this calculation. There's also a constant term here, but it doesn't matter in the minimization. It just drops out of the minimization and does not bother us. And exactly the same calculation gives us, going backwards, this form of jk star, a quadratic in the current state with some coefficients pk that are going to be computed analytically. There's also a constant term that depends on the variance of the disturbance, and the optimal policy is linear as a function of the state. And it's just a matter of carrying the calculation backwards here to verify that pk is generated by this recursion, starting with pn equal to 0 and going backwards. For every stage, we calculate these coefficients, and simultaneously, we calculate this linear policy coefficients Lk. So we do this calculation for k equals n minus 1. We do it for k equals n minus 2, and so on. And we have obtained at the end the optimal policy for the entire problem from 0 to time n minus 1. So that's the solution of this problem. And notice that at the critical points of this calculation, these disturbance terms do not matter. And what only matters is that the expected value is 0. We could generalize the problem to have a non-zero mean disturbance. And in that case, we would have to include this in the calculation and carry it along. And the formulas are going to be a little different, but the process is going to be pretty much the same.
Professor, I have a few questions. So here, the P and L's are just the coefficients, right? That we're
Yes.
recursively determining. Okay, Professor, as my question was, while we're defining the cost function, can you tell me what is the intuition between this term R times U square?
The intuition behind this choice here.
Yes.
Yeah, we want the size of control to be relatively small, and there are a number of issues, a number of reasons for that. We don't want the control to be very large because it may cost us a lot in some real sense, in some practical sense. The other is that there may be constraints on the control, and we want to keep this control small in order not to violate the constraint. For example, in this cruise control problem, the throttle can only push you so much, okay? It has a limit, an upper limit. So that's what this quadratic penalty serves, to keep the control small, not to violate the constraints. So that's basically, these are the basic reasons for a quadratic cost. It's not necessarily the best choice for every problem, but that's what we choose for this example, if for no other reason, for illustration purposes. This type of problem with a quadratic cost function in state and control is very popular, and there are, for every practical setting, there may be different reasons for just different ways to justify the quadratic cost.
Okay, Professor, I understand. Thank you.
Okay. So here we're focusing on the mathematical solution and the fact that the solution can be obtained analytically. It has a convenient form, linear policy, and quadratic cost. And as I mentioned, there are a number of there are generalizations, and the solution does not depend on the distribution of WK, only on the mean. In other words, we have certainty equivalence, and this certainty equivalence property carries out to more general linear quadratic formulations. Then we have considered one-dimensional problem, but we may have a multidimensional problem where we have several equations. For example, one equation may have to do with the velocity, and the other equation may have to do with the distance to the preceding car. In problems of self-driving cars and automated highways, the models are much more complicated than that. They involve not just a single system equation, but multiple system equations. However, as long as we have a linear system and a quadratic cost function, the character of the policy remains the same. We may have non-zero mean disturbances. there's a generalization to infinite horizon, which we're going to talk about shortly. There's another major generalization where the state of the system is observed partially through linear measurements. So in some cases, you may not know exactly the state, but you may estimate through measurements. And in that case, there is an extended form of certainty equivalence where you, even though you don't know the state, it's an uncertain quantity, you replace it by its expected value given the measurements, and you use the same linear coefficient for the control policy, and this expected value is provided by some estimator, and there's something called a Kalman filter, which I'm not going to get into, but it's a convenient estimator for calculating this expected value. And the important thing is that this extended form of certainty equivalence holds even for these problems. It's one of the central results of control theory. Now, of course, linear systems and quadratic costs are very nice assumptions and lead to an analytical solution. However, they're also a starting point for other lines of investigations and approximations. For example, there are linear quadratic formulations for problems that involve state and control constraints. These are more difficult problems, but the linear system and the quadratic costs still are convenient. And this type of problems arise in model predictive control. Also, a major difficulty, a far more complicated problem is a problem where the parameters change over time. For example, the B coefficient in the cruise control setting, the B coefficient relates to how much real force the throttle applies, the engine applies to the car. But that depends on a number of other things. It depends on how many passengers are out of the car. It depends on whether the car is going uphill or downhill. And all of this changes over time. So oftentimes we have to design a control system under conditions that are not known a priori, and they may be changing over time. And this is the subject of adaptive control, which we're going to discuss in the context of reinforcement learning and our methodology in the future. Still, in all this, linear quadratic formulations play a significant role, and we're going to encounter them as we go along again. Okay, so let's return to approximation in value space for the stochastic problem. And what we do is at a given state, we have to calculate a control. And we do this by minimizing the cost. The first stage cost is one step look ahead with a cost function approximation involving J tilde, some J tilde that we have calculated in some way. There are also other kinds of approximation that you can introduce in this minimization. You may try to simplify the expected value, which involves considerable computation, and you may try to simplify also the minimization. So there are three approximations involved in this scheme: cost to go approximation, expected value approximation, and some simplification in the minimization. There are some variants here. You may use multi-step look ahead here. And the expected value may be replaced by some certainty equivalent of WK. We're going to talk about an important class of simplification, which involves multi-agent systems, where the control consists of multiple components. And we're going to see there that we can simplify the calculation by doing the minimization one component at a time. Okay, so we're going to revisit these approximations as we go along. Here's an example of how we picked this J tilde by truncated rollout with some base policy and some terminal cost approximation, which are obtained by offline training. And this is the alpha 0 example, except that we use one step look ahead in this figure. So at xk, we look at all the possible next states, and including those that occur randomly due to the occurrence of wk. We run the base policy from each one of those, and then we add a terminal cost approximation at the end. And all of this, the cost of all this is our J tilde from xk plus 1. So this is just an example, and we're going to see other examples similar to the deterministic case that we looked at earlier. Okay, so now let's take a 15-minute break. It's going to be a working break. We can catch our breath, but you can also collect your questions. And there's also a challenge puzzle that I want you to think about if you wish. It's optional. It involves a chess match where a chess player plays against a computer program, a 2-game match. And here a win counts for 1, draw for 1/2, loss counts for 0. And if the match after the 2 games is drawn, it's 1-1, then you play sudden death games, and whoever wins the first game is the winner of the match. And now the chess player can choose to play in one of 2 possible styles. The first style is bold, risky play, which wins with some probability less than 1/2 and loses with a complementary probability. So there's no draw in bold play. It's uncompromising play, no draw. The other possibility is to play timid, in which case you can get a draw with some probability, but you can also lose with the complementary probability, and you can't win. The player gets to choose the style for the second game after seeing the outcome of the first game. So the player has feedback here in watching the progress of the game, and the computer is assumed to play the same. Cannot affect the style of play in the game. Okay, so the player plays worse than the computer on the average. Whether it plays bold or whether it plays timid, the probability of winning the match, winning a particular game, is less than 1/2. The player must play bold at least 1 game, because otherwise he cannot win. So I want you to speculate on the optimal policy of the player, and in particular, even though the player is worse than the computer, a worse player than the computer, is it possible to have a better than 50-50 chance to win the match? So let's come back in 15 minutes, and we're going to deal with your questions, and also we're going to discuss this puzzle. Okay, so see you in 15 minutes.
Hey, Professor, can I ask a quick question?
Yeah, go ahead.
So is it during any game, the probability of win is sampled from a uniform distribution from 0 to 1/2? Or
yes,
like is for each game? So it's not, probability win is not
for each
constant.
game individually, yes.
Okay, thank you.
Are there any questions about the previous slides before we go into this chess match problem? Okay, no questions, so we get.
Hi, Professor. I have one question.
Okay.
Yeah, I just want to know, can you simply describe the advantage of rollout algorithm? Because when I go over the dynamic programming, I found that when we want to find the optimal path, we start from the endpoint and backtrack to the start point, and then we can find the optimal path. But for the rollout, we use a heuristic algorithm to search, I think, search all the paths, and then we use rollout to find which path is the optimal path. So currently, I cannot find the different parts between the rollout algorithm and the dynamic programming. I know why we use the rollout algorithm, because when we use a dynamic programming, we have the dimensional curves. So that is why we choose the rollout. So, but currently I cannot find the different parts between the rollout algorithm and the dynamic programming. So I'm confused about why we choose the rollout algorithm.
No, there is a difference. If you look carefully at the rollout algorithm, you will see that it does not explore all the paths. It explores quite a few paths. It explores like, I think, 4 paths, whereas altogether there are 6 paths. But also in a larger problem with more cities, there would be a lot less paths that would be explored by rollout relative to the exact dynamic programming algorithm. And this is also part of your homework problem. You'll see that in a larger problem involving 5 cities, the rollout will explore a lot fewer paths than the dynamic programming algorithm. So check the computation, and if you still have a question, you may ask me privately.
Okay, sounds good. Thank you, Professor.
Okay. Any other question? Okay, so let's go to this chess puzzle. Who wants to say something? Can you comment on what you think the optimal solution is and why? And is it possible to have the player have a more than 50-50 chance of winning the match, even though it's a worse player?
My intuition was that the first play has to be a bold play, because otherwise, if you play timid, then it basically doesn't make sense, because you either are at the same spot where you started at, or your opponent has an advantage. So the first play has to be bold. And then if you lose, it has to be a bold play again, because if it's a timid, you stand 0 probability for winning. And otherwise, if you win, it makes sense to play timid, because I think like the probability comes out to be, higher for a win, because there's no way for the opponent to get like 1 point, or sorry, the other way. Yeah.
Right. Yeah. It's pretty clear that you have to play bold in the first game, because if you play timid, there's no way you can win, and you may lose. And if you draw, you're in the same place where you were with 1 game less. So clearly, you have to play bold in the first game. That's correct. Of course, you have to verify it mathematically, but intuition is pretty clear on this. And then you play bold in the first game, but if you lose, then the score is tied. And I'm sorry, if you lose, then you have to play bold again with aiming for the chance to tie, and then to play sudden death. So it's pretty clear that you start with bold play, and there are 2 possibilities. Either you win with probability, which happens with PW, in which case you have to play timid, okay? Because because in the case of a draw, you would get into presumably have a better chance to draw than to win, and then you would maximize your chances of winning the game, of winning the match. On the other hand, if you lose the first game, then you have to play bold. And the optimal policy, you can represent it with this graph here. Start here, play bold, and then if you win, you play timid after that. And then if you lose, you play bold. And you can verify this with a dynamic programming algorithm. And the calculations are given in one of my books. And you can access this particular, you can access 20% of the book through Google Books, and you can see the solution there, it's included. So let's accept that, that this is the optimal policy. And then the transition probabilities between different states are shown here. Is it possible that, the overall probability of winning the match is better than 50%? Well, how do you calculate this probability of winning the match? You have to draw all sequences of events. Here you win and then draw, and then you win the match with probability 1. So this branch of the tree has this probability PW plus PW plus PD, and then the probability of this branch is the product of these two probabilities, and so on. So from this tree, you can calculate the match win probability, and it turns out that it is possible with the right choice of PW and PD that you will get an overall probability that's better than 50%. And in fact, you can verify from this tree here that if PW is 0.45, okay, you win with probability 45% and you lose with probability 55%. And in PD equals 0.9, 90% of drawing and 1% of losing. With these numbers, then if you do this calculation, you'll find that the probability of winning the match is more than 50%. Now, what's the intuition for that? The player has an advantage against the computer in that it can choose, it can dictate the nature of play after the first game. The computer cannot adapt, cannot change its probabilities, but the player can. And so uses feedback, uses a policy as opposed to a sequence of plays that is chosen a priori without looking at the outcome of the first game. So that's the advantage. It's the advantage of feedback, the advantage of using a policy rather than sequence of decisions, which makes the difference here. Are there any questions?
I have a quick question. So this, I just wanted to check. So if we ran this simulation, or like using this policy, and we ran it 1,000 times, so with different realizations of PW and PD, there's no guarantee that 50% of the time the player would win, right?
Well, PD and PW are going to determine the outcome of the simulation.
Yeah.
And if you were to use 1 million times, 1 million runs of the simulation, as opposed to 1,000, then you would be almost essentially you would get the correct averaging result. There's no guarantee that you will win, but you have a better probability.
I see. I just, when I first saw the question, I thought it was asking for like, yeah, running over 1 million games with the optimal policy, will you be able to show that the player would win over 50% of the time with an optimal policy over a sufficient number of games? That's
exactly what, yeah, that's the result. If you were to play 1 million matches, okay, with, it's possible with these choices of probabilities to get a more than 50%. You'll get 53%. You'll get a win 53% of the million times, almost.
Oh, I see. I thought that PW and PD were sampled from a uniform distribution. So with that, we didn't necessarily choose them. Okay, my bad. My bad.
No, the outcome of the game is sampled from a distribution of 0.45, 0.55.
Mm-hmm. Yeah, got it. Sounds good.
Yeah. Okay. Okay, so let's now go into infinite horizon problems. Here, the number of stages is infinite, and we still have random transitions from one stage to the next, subject to uncertainty, and there's a cost for each transition, but it's multiplied with a discount factor. The same cost is counted less in the overall cost function as time goes forward. In other words, we count, we're not worried about high costs in the future. The costs in the future are discounted by this factor. This is in order, as you sum all these costs, in order to keep the overall cost finite, we introduce this discount factor. Now, this discount factor could be either equal to, could be less than 1, or could be equal to 1. And if it's less than 1, the problem is called discounted. And the cost of a policy over an infinite number of stages is the limit of the finite horizon costs. This is the expected cost of n stages. If you let n to go to infinity, you would think the cost of a policy starting from a given initial condition. And the optimal cost function is the minimum overall policies. It depends on the initial state. It's denoted by J star, and it's the optimal cost of running, starting from a state x0 and going forward for an infinite number of stages using this policy. Now, problems with a discount factor equal to 1 must have special structure to keep this cost from blowing up to infinity. They typically introduce a special termination state, which is cost-free, a state where if you reach it, you pay no cost and you stay there. Typically for these problems, also G is positive. Then, roughly speaking, the objective is to reach or to approach the termination state at minimum expected cost. Many problems in control theory are of this type. Shortest path problems or stochastic versions of shortest path problems are of this type, where there's a goal state that you would like to reach with minimum expected cost. And once you reach it, you pay no more cost. And usually, this shortest path type problems involve alpha equals to 1. So the cost of the policy is the limit of the finite horizon costs. So how do we approach this problem? Well, it makes sense to think that the n stages optimal costs approach the infinite horizon optimal costs as n, the length of the horizon, goes to infinity. So let's see where this intuition leads us. Let's consider the n stages version of the problem, and let's call Vn minus k to be the optimal cost to go starting at x and going for k stages. So this is given by dynamic programming. And we have to play a trick here. In dynamic programming, time runs backwards, right? From the terminal state backwards. And what we wanted, but in an infinite horizon problem, there is no terminal time. The horizon is infinite. So we have to modify our thinking about costs as they get incurred. So let's modify the dynamic programming algorithm so that it runs forwards rather than backwards with a change of notation. So we introduce this notation here. So Vn is the V sub n is the terminal cost, and we go backwards like this to Vn minus 1 and so on. And let's, in this equation, reverse the time index, divide with this alpha to the n minus k and do the calculations and call this j k sub x. Then we obtain this formula, which goes forwards. This is a dynamic programming for that algorithm that goes forwards and does not depend on the terminal state, the horizon n. So j sub n is equal to v sub 0, which is the n stages optimal cost starting from x, and jk sub x as given by this algorithm here gives you the k stages optimal cost starting from x. So with each iteration of this algorithm, you get the optimal cost of a longer problem, longer by one stage, from k stages to k plus 1 stages, k plus 2 stages, and as k goes to infinity, you expect to get the optimal cost of the infinite horizon problem for an infinite number of stages. That's what this expression says, that you can run the dynamic programming algorithm forward with a reversal of time index, and in the limit, you should get the optimal infinite horizon cost. Now, this is the intuition. It's true a lot of the time, not always, but for the problems that we are going to be considering, it will be true. So let's accept that as a working hypothesis for the time being. Now, you have this equation holding for all k. Take the limit here as k goes to infinity, which gives you in the limit j star here and j star here. Then you get this equation. This is the limiting form of this equation here. And this is an important equation. It's called Bellman's equation. It's you expect that it would be satisfied by the function j star. There is some question mark about that. A mathematician may question that, but it is almost always true, certainly true for the problems that we are going to be discussing. So if you can solve this equation, you'll find j star. However, this is not a trivial equation. It involves an equation for every x. So if x is 1,000,000, there are 1,000,000 equations here. If x takes values in a continuum, then there's an infinity of equations here. It is a functional equation and not trivial. However, it's the fundamental equation from which everything else flows. Notice that alpha came here through this calculation. And basically, there's an intuition that you can use to understand what this equation says. It says that if you are at state x, the optimal cost from that x with optimal choice of policy should be the minimum of going to through the first stage, paying the corresponding cost, and then add the cost, the optimal cost of the remaining stages from the state where you land, but also discounted, because with every stage there's discounting of alpha. So you can verify, and you can think through about the fact that there should be an alpha over here. So there's an intuitive way to see this equation, which is very fundamental, like I said. And now this equation, if you can solve it, if you can find j star, then you can obtain an optimal policy by minimizing for every x and calling the corresponding control mu stars of x. So if mu stars of x attains the minimum in this equation for every x, then this policy is optimal. Now notice that this policy does not depend on the time index. That's the policy, the optimal policy that you would use at stage 1, at stage 2, at any stage. It's called stationary. And the reason is that everything here does not depend on K. This does not depend on K. This does not depend on K. The state space and the control space stay the same. So if you are at a given state, whether you are at time 0 or whether you are at time 10, you're seeing the same problem ahead of you. And therefore, it's reasonable to expect that you would use the same optimal policy. Now, these are the three theorems, the three basic theorems that you expect to hold in any kind of infinite horizon dynamic programming problem. You get the optimal cost function in the limit by taking the limit of the finite horizon optimal costs, and you generate this costs, this finite horizon cost, through this algorithm here, which is called value iteration, and we're going to see it in the next slide also. So, value iteration converges is the first theorem. Bellman equation holds is the second theorem. Third equation is that the optimal policy, third theorem is that the optimal policy is stationary, and it's obtained by minimizing in this Bellman equation, the right-hand side of Bellman's equation. These theorems do not hold always. They will hold for every problem that we're going to be discussing. They are the subject of theory. The theory of infinite horizon dynamic programming revolves around these theorems, guaranteeing that they hold under the right conditions. And the theory of infinite horizon dynamic programming involves also two algorithms that are fundamental. The first algorithm is the value iteration algorithm and generates the finite horizon optimal costs one stage longer at with every iteration. And it turns out that this algorithm is often valid even for an arbitrary J0 or from a convenient class of functions J0 that to start. So even for almost arbitrary initial function, you crank forward these functions and that's the value iteration algorithm, and you expect it to converge to J star. And I put some question marks here because that's not always true, although it will be true for the problems that we're going to be discussing. The second major algorithm is policy iteration. This algorithm here generates a sequence of functions, the JKs. This algorithm generates a sequence of policies, mu k. These are the players that I was talking about in the last lecture about alpha 0, the sequence of players. They are policies, and the kth policy in this sequence is denoted by mu of k, superscript k. And it also generates the cost functions of those policies, starting with some more or less arbitrary policy. And the main result here is that J mu k's converge to J star. You get the optimal policy in the limit. So how does this policy iteration algorithm work? The typical iteration starts with some initial policy mu 0, with some initial the typical iteration starts with a current policy mu and generates a new policy, which we call mu tilde, in 2 steps. The policy evaluation step, which computes the cost function of this policy mu. We also call this policy base policy. The new policy is called the rollout policy. And it's obtained by this policy improvement operation, which computes mu tilde by using 1-step look-ahead minimization, but with the terminal cost being J mu. Okay, so from the first step, I calculate the function J mu as a function of X, and I plug it here in this minimization in place of J star. We use the current base policy, and we minimize here, and we obtain a new policy. So from mu 0, I get mu 1. From mu 1, I get mu 2, and so on. I generate a sequence and a corresponding sequence of cost functions. And the result basically is that this sequence of policies converges to an optimal policy, and that this J mu case converges to J star. Okay. Now, this algorithm is more sophisticated, more time consuming per iteration than this one, but converges much faster, it turns out, and we're going to see why. But involves some major difficulties. Given a policy, how do we compute this cost function of the policy? Well, for policy evaluation, we can look at the Bellman equation for the policy. This is the same as the Bellman equation for the overall problem, but involves only one policy, this policy mu. And it has this form here. It does not involve minimization. Instead, it involves only mu of x. And it turns out that using the same kind of reasoning as we did in the previous slide, that this is the Bellman equation that should be satisfied by J mu. Now, this equation is simpler than the Bellman equation for the overall problem, which we call the min Bellman equation. We call this the mu Bellman equation. The min Bellman equation involves a minimization here, which makes it complicated and non-linear. It turns out, and you can see that this equation is actually linear. If you double J mu, you're going in here, you're going to double the overall expression. So it is the expectation is a linear operation, and so this equation is linear. So for a finite number of states, let's say n states, this can be written as n linear equations with n unknowns, the cost of the corresponding states, and can be solved for small problems, can be solved by MATLAB. Okay, it's simply solving a system of linear equations. So that's one way to solve the Bellman equation. Not that it is easy for a large dimensional problem, for a problem with many states, but it is one way to do it. The other possibility is to calculate the needed values in here to find, okay, in this one-step look ahead minimization, you need J mu from some next state. You can run a Monte Carlo simulation from that next state using the policy and average the results to get the expected value of that. That's another possibility. Use simulation to calculate the needed values in this one-step look ahead. And there are also methods for doing this. Approximately, there are some other more sophisticated reinforcement learning methods called temporal difference, which we may get into sometime later. But these are the two basic methods. Solve the Bellman equation. It's also possible to solve it either by MATLAB, or you can solve it using value iteration. Crank this iteration here, but without the minimization, with mu of x instead. That would be another way to do it, to solve the Bellman equation iteratively. So all of this suggests that this policy iteration algorithm is more sophisticated, more time-consuming than this algorithm. On the other hand, we're going to see that it is much faster. And it's also better suited for approximations of the type that we do in reinforcement learning. So here's a schematic for exact policy iteration. Yes, somebody said something.
Yes, so in the policy improvement, so what is the difference between, like, when we are finding the policy improvement step, we are finding the new policy. So what is the difference between value iteration and the policy improvement? Because you said in the policy improvement, we use one step look ahead to find the new policy. And
yes,
in the value iteration, we are actually performing the minimization based on the control policies, like the policy again. So what's the difference between policy improvement and the value iteration?
Yeah, the amount of difficulty in carrying out this minimization is comparable. On the other hand, you expect to do this a lot fewer times because you're using the J mu here. That's the basic difference. we're talking here about exact calculations, right? Exact dynamic programming, solving the problem exactly, not with about approximations. This may take you millions of iterations to converge. This usually converges in a handful of iterations, 5, 10, 20, something like that.
So you mean in the one step look ahead, we actually improving our policy. So we changing our complete policy. Like we have a policy means we have the control operations for all the time steps, and then policy improvement means we find the new operations, control operations for all the time steps.
Well, because the policy that you find is stationary, you only have to do it for one time step, but you have to do it for all states.
Yes, okay, I got it. Thank you, Professor.
Just one moment. I'm going to try to improve the audio here because I can't hear your questions very well. I'm going to try to use a different speaker. Okay, can you hear me now?
Yes, Professor, we can hear you.
Okay, hopefully. Okay, somehow I'm not getting, I'm not hearing you very well. I can't understand why this is so. Anyway, we'll continue. So we have three theorems. Three theorems and two algorithms. And going back to policy iteration, this is a schematic of the exact form. We have a base policy. We evaluate it by any of the number of the methods that we discussed to get J mu, its cost function. And then we do a policy improvement to obtain the rollout policy. And then we repeat with the rollout policy in place of the base policy. That's the algorithm. Like I said, it's very time consuming. Both of these can be very, very time consuming, and this can be very, very time consuming. However, this algorithm has some theoretical properties that we can prove. There's a lot of theory around it, in fact. In the limit, it yields usually, although perhaps not always, an optimal policy. In theory, if you can carry out this algorithm exactly with exact calculations. And in the limit, as you do an infinite number of policy iterations. Policy iteration is faster than value iteration, and we're going to interpret it as Newton's method for solving Bellman's equation. That's why it's faster, because it's Newton's method, and Newton's method is very powerful. Now, for approximate implementation, you can approximate these calculations here, obtain this function here and this policy approximately through using by using data and some approximation architecture like a neural network. So you have the base policy, you collect a lot of data, performance data, samples of its cost function from various states, and then you fit a neural network to that to obtain an approximation to this J mu. Then you use this J mu to generate corresponding one step look ahead policy samples, and then you fit those samples with a policy from some class in a policy network. Sometimes you don't use a policy network, but you use a value network only. That happens in TD Gammon. In AlphaZero, there's a policy network and a value network that are used to approximate this and to approximate that step. And then you get an approximate rollout policy that you can use to start, again, a new iteration. So that's the schematic. That's the way to think that's one way to think about exact and approximate policy iteration. And then you can ask questions about how each box is going to be implemented. Okay, so now let me give you an idea about an abstract view of dynamic programming that is going to play some role in our context, particularly starting in the next couple of lectures. Bellman equation has a right-hand side, which is a function, and the left-hand side, which is also a function. So this expression here can be viewed as a map, an operator that takes a function J star and maps it into another function. And the equation says that if you operate with this operator on J star, you'll get just J star just again. So you can write this equation as a fixed point equation in the following form, where T is the Bellman operator that transforms a function J into a function T sub J. And it has this form. You plug in J here, you get a T sub J, a function of X. And it's an operator, and you can view it as a subroutine, okay? You feed it some input and there's some output that comes here. And the Bellman equation says that J star is a fixed point of that operator. So this is also a shorthand way to write Bellman's equation, which is rather long. You write as J star equals Tj star. And there's a shorthand theory that goes with everything that is of interest in dynamic programming that uses these Bellman operators. Value iteration is simply this. From Jk, you get T sub Jk for the next iteration. So it can be viewed as an iteration for solving a fixed point problem. The fixed point problem being the J star equals Tj star. Also, for every policy, there's a Bellman operator that corresponds to it and corresponding Bellman equation. So the operator that corresponds to mu, the mu Bellman operator, is this T mu here. It maps a J into a T mu sub J through this expression here. And in particular, J mu, according to the Bellman equation, is a fixed point of this T mu. So there are two operators here, the min Bellman operator that involves the minimization and the mu Bellman operator that does not involve minimization and it's associated with a policy mu. And there's a nice and convenient way to write policy iterations compactly. We are at a certain base policy, mu k. We evaluate it by finding a fixed point of this mu k Bellman operator. And then we improve it by finding mu k plus 1 that satisfies this expression here. It's the mu k plus 1 that attains the minimum, okay, the minimum here when J star is replaced by mu k. So all the important components of the theory can be expressed compactly and conveniently using operators. And this is nice if you want to work out mathematical proofs or to eyeball various calculations in a succinct way. But it's also very nice from the point of view of visualization. And we're going to do a little bit of that shortly, but a lot more in the future. So that's what I'm saying. The abstract view is very useful for theoretical analysis, intuition, and visualization. So let's forget about these operators for the time being and look at them in a simpler context. In the context of a linear quadratic problem, which is also deterministic. So we don't have to carry these W's, these disturbances and these expectations. We're going to make the problem deterministic. After all, certainty equivalence holds for this problem. So you can really analyze it by looking at its deterministic version, although the random disturbances have been set to 0, their expected value. So this is the system we're looking at here. There's no WK. It's a quadratic cost per stage, the same that we had before. Again, we look at one-dimensional version of this problem in order to simplify the calculations for the purpose of this lecture. And we consider the undiscounted version of the problem where alpha is equal to 1. Now there's a termination here, state 0 is a termination state, so this is a problem where we can't get away without any discount factor. So this is our system equation, the quadratic cost, and the Bellman equation. So we're looking at an infinite horizon version of the cost of the problem we looked before, except that there's no disturbance. Now, for the finite horizon case, we got an optimal cost function that was quadratic in the state, and a policy, and an optimal policy which was linear in the state. So this suggests the form of the results for the infinite horizon problem. J stars of X, you expect that it will be a quadratic of the state, where K star is some positive scalar that remains to be determined. And you also expect that the optimal policy is linear of this form here, a linear function of the state, where L star is some scalar. And now, how do we characterize this K star? Well, we plug into the Bellman equation. Now here's the Bellman equation if J's of X, for J's of X being the generic quadratic. K is any positive scalar. So we restrict attention to quadratic functions and we write the Bellman equation. Now this Bellman equation has the favorable structure that we witnessed in the finite horizon case. It involves a quadratic minimization with respect to control, and after you compute the minimizing control and plug it in, you get a quadratic function of the state. So we can do this calculation in closed form, plug in the result, the minimizing u, and carry along the calculation, and we get this final result. And this is a very similar calculation to the one what we did for finite horizon problems, and I'm not going to show it here. I'm going to show you the result. This f of k is a function of k, and it has this form, which is reminiscent of the form of the finite horizon case. And the minimizing u is the one from this equation here, is given by this expression, a linear expression of x. So the minimizing u suggests a linear policy, with this being the linear cost coefficient. So the Bellman equation is solved by K star that is such that K star x squared is equal to f of K star x squared, or K star equals f of K star. The x squares drop out from here. So the Bellman equation becomes K equals f of K. And this is called the Riccati equation. Bellman equation is this one. After you drop out the x stars, it becomes the Riccati equation, which has this form here. K star equals to this expression of K star. Now this is a nonlinear equation. It's quadratic actually in K star. And if you can solve it, you obtain K star. Moreover, from the Bellman equation, we minimize with respect to u with K star in place of K, and we obtain the corresponding optimal policy, which is linear of this form here with K equal to K star. That's the solution of this problem. If you can solve this Riccati equation for K star, you will have found the optimal cost function. And in the process also, after finding K star, you obtain the optimal policy as a stationary policy, which is a linear function of the state. A very basic result, a very important result, and it is the limiting version of the finite horizon result. Okay. Are there any questions here? So we want to solve this infinite horizon problem, and we want to find the optimal cost function, which we have suggested that it is quadratic with this k star related to the Riccati equation. How do we solve the Riccati equation? Well, for a multidimensional problem involving a multidimensional system, you would need to do some calculation that's kind of complicated. But the advantage of working with a one-dimensional problem is that you can solve this equation graphically. And here's a graphical solution. K star is a solution of this Riccati equation. And the Riccati equation involves this right-hand side, f, and it is given by this expression here. This is the A and B coefficients of the system, R and Q coefficients of the cost. And you can plot, and this is a pretty accurate depiction of this function. It is concave. It asymptotically goes to this level. And you can see that by taking k to go to infinity. If k goes to infinity, then this R term drops out. And then what you get in the limit is this expression here. And it is monotonically increasing with k. So the red graph, the graph of the f function approaches this asymptote. On the left side, as k goes to minus infinity and approaches the point where the denominator is positive, where the denominator approaches 0, okay? Still positive, but approaches 0. Then it drops down to an asymptote around this point here. So that's the graph of this f function. Now we want to find a fixed point of this f, a k star that is equal to f of k star. So the right-hand side of this equation is this red graph. The left-hand side of the equation is just a straight line, the 45-degree line. And at the point where the right side graph and the left side graph intersect, you obtain a solution of the equation. Now, one of the intricacies here is that this is a quadratic equation that has two solutions. In general, for a multidimensional problem, we have even more, we'll have more than two solutions actually. But even in the one-dimensional case, there are two solutions, and one is positive and the other is negative. This is always true, okay? Because like I said, this depiction here is realistic. There's one positive solution and one negative solution, but only the positive solution is of interest because the optimal cost, we know that it is positive. So this solution does not matter and it's unrelated to the problem, we just disregard it. So it's a common way to represent the solution of fixed point problems. You plot the right-hand side and you plot the left-hand side and you find the points of intersection, and this gives you the solution. And it works very well for the case of the Riccati equation. Somebody?
Yeah, can I ask a question? We are basically solving the equation imposing a structure of J. So like, how do we guarantee that this is not a suboptimal solution that's optimal only in the space of quadratic functions?
Okay, that's a good question. This Riccati equation is Bellman's equation on the space of quadratic functions. So it's equivalent with the Bellman equation on the space of quadratic functions. So we found a solution through this process. We found a solution within the space of quadratic functions. How do we know that it is the optimal cost function and not something suboptimal? It is a non-quadratic function that is actually the optimal cost function. It's not evident from this figure. This figure just looks at a subspace of functions, the quadratic functions. So there's no guarantee from our analysis so far that the optimal cost function is quadratic. However, you can verify by some additional analysis, which to represent sufficient conditions for a certain cost function to be the optimal cost function. And you can verify the sufficient conditions, and you can prove that actually this is optimal. But we're not going to prove it here.
Okay, thank you.
So, so that's the solution of the Riccati equation. It involves this fixed point structure here. And now let's look at other operations. We're going to look at how value iteration can be interpreted within this Riccati equation figure. So what is a value iteration? Remember, value iteration generates from JK, it obtains JK plus 1. And this JK plus 1 is the K plus 1 iterate, whereas JK is what you obtain from the Riccati operator at KK. So if you write the form of value iteration, it involves this Riccati operator, and it has this form. And if you cancel out this x squared, you obtain value iteration in the space of quadratic functions. Starting from a quadratic function, you get a new quadratic function and a new quadratic function with quadratic cost coefficient kk, kk plus 1, and so on. So that's value iteration in the space of quadratic functions. And we represent it here in this figure as follows. We are at the typical starting point of an iteration, kk. We start at some point, k0, some positive point of 0, k0. At the typical step, you have kk. And you calculate f of kk. Now, f of kk is this level here. You reflect this level across the 45-degree line, and that gives you kk plus 1, right? Kk plus 1 is equal to this level here. But this is equal to that, right? Because it's a 45-degree line. So that's the way you get kk plus 1. And now you apply f to it, and you go to this point. And you go horizontally, reflect down to the reflect vertically to the horizontal axis, and you get kk plus 2, kk plus 3, and so on. So this is a typical staircase structure that you encounter in graphical depictions of fixed point iterations. Start somewhere, go up horizontally, up again, and so on. And you can see from this figure that if you start anywhere from any positive initial point, then you're going to converge to this point, k star. If you start from anything that's on this side of the axis, larger than k star, again, you're going to converge to k star. In fact, faster. Even if you start from a negative initial condition, you're still going to converge to k star. If you start from an initial condition that's not only negative, but also smaller than this asymptote here, you are going to converge smaller than this point, this other solution, then you're going to converge to the solution k bar. On the other hand, from the starting points that make sense, which are the non-negative starting points, you're going to converge to k star, and that's a justification for value iteration for the case, again, the one-dimensional case, a graphical justification of value iteration for the one-dimensional linear quadratic problem. All of these results hold true even if you have a multidimensional system. In other words, instead of a state variable, you have a state vector consisting of multiple state variables. And all of these results hold. The analysis is a little more difficult. It involves some proofs. It involves matrix algebra. We are going to use here the linear quadratic problem for intuition and also for visualization. Visualization, like we saw here, and also in the previous slide. And in the next lecture, we're going to look at policy iteration, how it relates to this figure. And we're going to see that policy iteration is Newton's method for finding this fixed point, the solution of this equation. It's going to involve linearization, and then linearization, solution of the linearized problem, and then another linearization again, and so on. And we'll see that it converges very fast and also provides a lot of intuition about what happens when you do approximation value space, or when you do rollout and things like that. So this is the last slide. And let me say a few things about what we're going to do in the next lecture. We're going to look at linear quadratic problems again, and look at the Newton step interpretations that I have alluded to so far. We're going to view approximation in value space as a Newton step for solving the Riccati equation. We're going to view rollout as a Newton step starting with a particular starting point, the quadratic cost coefficient of a linear base points. And we're going to view policy iteration as repeated Newton steps. And all of these are going to give us intuition about what makes these methods work fast. It's going to revolve around these interpretations based on Newton's method. So that's going to be one part of the lecture. And then we're going to go into examples of problem formulations and reformulations. I know that many of you are interested in how all this theory that I've been talking about relates to your own problems. How about some examples? Well, we gave the graphical salesman example, we gave the linear quadratic example, but there are so many other problems that we want to address. And there's an interesting issue as to how do we formulate problems so that they are solvable and solvable conveniently by dynamic programming or approximate dynamic programming. We're going to discuss problems that involve a terminal state, like shortest path problems and stochastic versions of shortest path problems that involve a goal state. We're going to talk about problems that have unusual dynamics that may involve delays in the evolution of the state variable. So xk plus 1 is affected not only by xk, but also by xk minus 1 or xk minus 2. There are delays in the system equation. We're going to see how we can reformulate problems like that in their usual format. Other types of characteristics, problem characteristics that we have not addressed, like I have implicitly assumed that the WKs, the stochastic disturbances, are independent from one stage to the next. What happens if they're correlated? We're going to try to deal with that by reducing the problem into the one that we know how to deal with, to something called state augmentation. There are many, many different problems that are more complicated than the ones that we have discussed, but can be reformulated in the format that we have discussed. And the process is called state augmentation. And it's very convenient because it allows us to apply the general theory to more complicated problems. I don't know if we're going to go through this entire list, but on the horizon, in our schedule, perhaps in next lecture, or perhaps in the lecture after that, we're going to discuss problems with imperfect state information, where the policy does not depend on just the current state, but also depends on previous states, and also if the state observation is imperfect. Instead of observing the state, we make measurements that are related to the state, and we collect these measurements, and we have to make decisions in using these measurements. We're going to talk about multi-agent problems involving separate decisions and actions from a multitude of decision makers, which we call agents. Now, the minimization over the control becomes very complicated for these problems. We're going to see how we can formulate them so that approximation algorithms can be used that do not require a lot of computation, overwhelming computation. We're going to say a few things about systems with changing parameters and adaptive control, and also model predictive control. We are likely not going to be able to cover everything here, but whatever we don't cover, we're going to cover 2 lectures from now. And all of this is in the class notes, our discussion for this next 2 lectures, and the next 3 lectures, in fact, are in the class notes, sections 1.5 and 1.6, and I suggest that you take a look at them as much as possible, AMIP. There's also a homework that is exercise 1.1 of the class notes. This is a traveling salesman problem that involves 5 cities instead of 4, and you are asked to do the computations, the exact dynamic programming computations, as well as the approximate dynamic programming computations using the rollout algorithm. So that's your first homework. It's going to be due 1 week from now, Wednesday night next week. So that's all I have for today. Are there any questions? Okay, so let's us adjourn, and we'll see you next week.